To look at the dozen most common areas of defect found in traditional buildings, plus a couple of specialist ones, and then we're going to talk through a case study on planning and procuring masonry works. And really we don't have much time, so I'm only going to give you the headlines for each of my topics, and I'd like you to stop me whenever you want more detail or ask questions at the end. My 12 topics are in no special order, but we will start at the top of the building and just quick look at fireplaces and flues. Fires will smoke unless you use the correct ratio of fireplace opening area and flue area. There is no other magic to it. Of course there are other influences like trees next to the building and all that kind of thing, but use these ratios. I understand these papers are being distributed afterwards. So I'm trying here just to give you a few little helpful bits and bobs that you can take away with you. Stick to these ratios, and with a bit of luck your fireplace will not smoke. If it does, look further up the flue, look at the way the chimney is constructed, the pot's put on, the cowl is fitted, and all those kinds of things. Moving straight on, I want to talk a little bit about rolled sheet roofs, lead and copper work. I'm not going to worry about other forms of lead and copper. I'm just going to talk about rolled sheet, because unless there's a special requirement to talk about slab or anything else, these are the most usual materials you're going to come across. And the first thing to remember, of course, is that flat roofs are not flat. You need a minimum of 3 degrees of slope to allow the water to run off. And both these materials have quite large coefficients of linear expansion at around 20 degrees. I'm not going to go into the technical of that, but in effect, if you compare quartz, which is very stable, 0.3, water, which is not stable, it freezes and expands and moves thermally, 69. Lead is 29, copper is 17. They're both quite mobile materials. So these materials must be allowed to move. Bay size is critical, as is a suitable underfelt slip plane. So you give it a slip plane on which to move, and you allow it to move. I'm going to show you slides in a minute, but flat roofs must either be vented cold roofs or vented warm roofs. And the common factor is, of course, ventilation. If you don't have ventilation, you'll have what's called interstitial condensation. Interstitial meaning that the condensate, the water, is actually dropped within the fabric of the roof. Now I'm going to come back to talk about that later, but flat roofs covered in metal must be vented either above the insulation or below the insulation. This, these two little coloured pictures here are from a brilliant little book. If you do work on historic buildings, get this little book. It comes from the Lead Sheet Association. Lots of useful little diagrams. If you stick to them, you really won't go far wrong. And the top left table what's really important about this is it sets out for you the bay length you need before a step when you're using code 6, code 7, code 8 lead. 2¼ meters before you have a step, 2½ meters before you have a step, and if you need a 3 meter bay, you've got to make it in code 8 lead. Now, do we all know where the coding comes from? A square foot of code 8 lead weighs 8 pounds. A square foot of code 6 lead obviously then weighs 6 pounds. So what you're talking about is the thickness of the lead, allowing you to get extra bay length before you need a drip. So if we look at a roof, this is all actually the same building, work we were doing 2 years ago. The large roof is code 7. The trim with the ventilation detail circled is code 5, and the gutters are code 7 again. We have ventilation hidden in here around the chimneys and along the edges, along the margins. You'd never know it was there, but it is there and it's absolutely vital. This picture was taken, the main picture was taken before the lead had settled, so you can still see where it was rolled out. You can see the little bits of water there, and you'd think, right, that's not laid at 3 degrees, but it is. It's just that it's going to take a little while for the lead to just settle down. If your bays are too long, your lead will expand and contract, and it will wrinkle and stretch and wrinkle and stretch until it fatigues through, and obviously it'll let water through. Moving on, this is a bit of an odd one to come straight on to, but architectural metalwork and galvanic corrosion. The first thing is always, always, always maintain your rainwater goods. It's the most common source of water ingress, and water leaking out of rainwater goods at the foot of the building is actually a very common source of subsidence as well. It washes out the fines, and the building then is inadequately supported. Now, galvanic corrosion, you may never come across it, but it occurs when two dissimilar metals are electrically connected in a conductive environment. It needs oxygen as well. The more noble metal becomes a cathode and is protected, the more active metal becomes an anode, and its corrosion is accelerated. This doesn't matter for most of us most of the time, but if you come across wrought iron, it matters very much. Wrought iron is special. It's rare. It's wonderful when you come across it. It's generally early because nobody's made wrought iron for a couple of centuries, I think. It's generally to be preserved. Repairs made with more noble metals such as modern iron and steel accelerate its decay, rot it. So don't do it, ever. Where wrought iron must be repaired using a modern iron, there is actually one way out of it, which is to introduce a sacrificial anode, which is anodic to both metals, and conveniently zinc is anodic to most things. It's quite low down the table, and you can in fact use a galvanized piece of steel where you absolutely must support a bit of wrought iron. Exterior paintwork. I'm not going to dwell on this. I'm simply going to say consider micaceous iron oxide for metal work, especially cast iron gutters and downpipes. It looks a bit like lead when it's finished, but it offers excellent protection to cast iron. For other materials, paint on the exterior of a building should be breathable and flexible. And in order of preference, this is as far as I'm going on paints today. For timber, go right back to linseed-based paints. I'm not here advocating white lead. In some circumstances I might, but for today I'm going to say linseed-based paints are fantastic. Available, a lot of them are Scandinavian. Wood stains, Solignum and others, not a bad second. They're microporous clearly. And you can go for a technical system. There's a Johnston Storm Shield, which is quite a good one. There are plenty of others. What they're trying to do is be stretchy and microporous, which is quite a tall order, when in fact linseed oil does it anyway. With masonry, lime-based paints. You almost don't need anything else. There are some quite good technical systems where you want a heavier paint, and Kime is one of those. But the key really is breathable and flexible. I'm going to move straight on to slating and tiling. The things to be careful of here, and I'm sure most of you know already, pitch. You're not going to, it's going to be much more difficult to keep the water out of a low pitched roof than a steep pitched roof. A lot of our older buildings have steeper pitched roofs. They have survived. There may have been other buildings with lower pitches built at the same time which we've lost. Headlap. If you are working on a lower pitch, you need to increase the headlap. Support. In Scotland, of course, we're used to sarking, fully sarked roofs, and we do less on tiling battens. And I'm English, but I think the Scottish roof is just the most wonderful structure. It's very, very, very well built, and I'm going to talk in a minute about Scotch slate. underlay and under easing, I don't know what's happened to the size of my text here. It's slipped, I think, since I wrote it, but there we are. Even though you're going to puncture this membrane with every nail that holds on every slate, it's actually still worth having. It does stop a bit of the draft, it does stop some of the moisture and push it down the roof. Clearly, if you're not going to have a condensation problem in the roof, it needs to be breathable, so you need to use a breathable membrane. Tilting fillet, under easing at the bottom, doesn't need to be breathable, needs to drop into the gutter. And what that's doing is it's taking all the water that does catch on the membrane all the way down and sliding it over a piece of standard roofing felt will do into the gutter. If you don't have an under easing, you're likely then to allow water through the nail holes to get into your wall head, wall plate and wall head. So it's a really easy thing to put in, it's a really easy thing to forget to put in. As is the tilting fillet. The picture on the next page will show you about that. Margins, I could spend a lot of time talking about slate and a half and the way to deal with abutments. The safest way with historic buildings where you're abutting up to a little water table or parapet or whatever is always the open water gate. It's the simplest, it's the one you can see if it gets damaged or blocked or anything, and it is open for the water to come down. And where the roof, which is going to move, it's sitting on timber, it's going to move much more than stone at the margin. Clearly, having that little piece of lead, which will allow the slates to move to and fro, is much better than having something like a mortar skew, which is just going to break. Nails, I've put a little picture here of some nails. The right hand two are bright, round, modern copper nails. The left hand three actually came off a roof on one of the royal farms. They are 200 years old, and you could pop them back in and fix another slate for another 200 years. There is no point in using iron nails, even if they're galvanized. The cost of copper it's more clearly, but it extends the life of your roof so much that it is absolutely worth it. One of the troubles with a galvanized nail, especially if your slate is quite rough, is that over the years it will rub and chafe on the collar of the nail. It'll take the galvanizing off, and the nail head will pop off, and you've lost it. Because copper doesn't depend on it, it's a softer metal, but it doesn't depend on that galvanizing coat, so you're kind of better off all round. If you can use stainless steel pins to hold the timber together as well, so much the better. Scotch slate, a quick word on that. The most fantastic roof. Graduated beds, so you'll see the slates at the bottom are larger. This is actually my own roof at home. And much smaller slates up at the top. Each of those is secured with just one nail. So if you lose one, you can swing them apart, pop a new slate in, one nail, and you're back with a complete roof. It's socked underneath, so I can put a nail wherever I want to put a nail. That roof will last 250 years, no problem at all. There isn't another roof that will. I'm going to just ask somebody at the front, David, would you just take the bag there and just feel inside the bag. All I want to know, I don't want to know what it is, I know very well what it is. There's a piece of building material in there. Is it dry or wet? We're going to need to know that in a minute. So whiz it round, is it dry or wet? That's all you need to know, pass it on.
Dry.
Okay, and on and on and on. Just so anyone who wants to feel it for themselves, all I need to know is whether it's dry or wet. So on with roofs while you're doing that. Top left, I'm looking down the inside of a sarked roof, and you can see the ends of the nails. So when you're doing a survey, look for that. That is an iron cut nail, square in section. Obviously, you can see where a roof's been repaired using either copper, galvanized, or whatever. That's the place to look to see what you've got. The right-hand picture is a building we're working on at the moment. This section of roof is on battens and is less than 200 years old. That other roof is fully socked and over 200 years old. We're actually going to have to re-roof the bit that's on the battens, and we can repair the bit that's on the sarking. Very special building, that one. This one here, simple problem, no tilting fillet. So, you've got 2 layers of slate coming down a roof, lapped. If you don't put something 1 slate thick at the bottom, you're going to end up with a weakness just above the gutter. And then a roof, this kind of roof, the bottom right, the kind of roof we see very often, it's been patched up, we've got mastic and we've got tingles. So this little tuck of lead here, that's pinned a little higher up and is used to hold a loose slate in. When you look at a roof, you're not always going to be able to get close to it. You might need field glasses. You're looking for tingles, you're looking for wire tingles. Sometimes you're looking for copper wire tingles. Sometimes you're looking for hooks. And they're all clues that you've got probably nail failure, sometimes crumbling slate where a nail hole just pulls to the edge. Right, on to rot. I'm not going to spend much time on wet rot. We know the fungus. It requires 43% moisture. So it's only going to occur in those, the jambs of the windowsill, the jambs and the sill of the window, dukes into walls, other such places. Like end grain. The timber goes soft, cracks follow the grain. I'm sure you all know exactly what you're looking for with wet rot. There are other wet rot fungi, and there are quite a range of harmless fungi, and you'll see them when you're out and about doing surveys, pezizas and that kind of thing, indicative of conditions where fungi will grow, but not in themselves alarming at all. Dry rot, though, great source of work for us. Its origin is interesting. It was brought over by Victorian plant collectors. It didn't exist in the UK at all until the Victorians went collecting plants, thought to have come from the Himalayas. It likes food and water in cool, still pockets, and it hates ventilation. So when it arrived here in Victorian times and found all those pokey little attics and roofs and little spaces with very little air movement, it was at home, and it has gobbled up many thousands of our best buildings. The mycelium are extraordinary. You put them on a dish in perfect conditions, they'll grow at 4 millimetres a day. A metre a year is perfectly normal. And the fruiting body, I've got a corker on the next slide, it can emit 8 million spores a day. Now, every breath you take, even in a modern building like this, will have dry rot spores in it. They are everywhere. You can't prevent the spores from landing. All you can do is stop them from growing. It's usually visible and detectable by smell. It breaks down cellulose, timber shrinks and cracks into cubes. I'm sure you've seen it. As I say again, ventilation, ventilation. Here we've got some lovely examples. Top left, the building, in fact, with that new lead roof. This outbreak occurred at the bottom of a blocked flue. So it was a nursery flue, not correctly blocked. Moisture got in, tracked down, got into this lintel, and there it is, rotting away. The bottom picture just shows the typical cubes, which are, as I say, I'm sure you know. The bottom right picture is a real corker of a fruiting body. They're not normally as sort of delicious as that. That one is certainly doing 800 million spores a day, or was. Just above it, the one with that little bit of decorative frieze, that is a bathroom. That's one we only looked at last week. My assistant had been to see it the week before, and as I approached this room, he said, "Oh yes, this is the room with the dry rot." I opened the door, and it didn't hit me. No smell. So I looked very carefully at the dry rot, fruiting body. I gave it a wee prod, and it broke off like a biscuit. I'd been in the floor above, and I knew there was a bathroom in the floor above, and I knew it served a should we say, late teen boy's bedroom. And I asked the owner of the house, "How long has your son been away, and the answer was he left before Christmas, and so the bathroom's not been used. It's a plumbing leak that's caused the problem, and it's dried up, and it's actually killed the dry rot. It's still a problem to resolve structurally, but the dry rot is dead. Quickly on to wood-boring insects, and you can't talk about them without talking about bats. Really speedy. Common furniture beetle makes a small hole. Deathwatch beetle makes a slightly bigger hole. House longhorn beetle makes a horrible mess. Look for dust to see whether it's live or not. Little bits of dust streaming out of the holes is a good sign that they're in there being active. And look for dead insects to see what they are. Treat with organic solvent or paste, and remember that treatments do not last forever. If you go to a house and they say, well, this has been treated, still look for active insects. All bats, of course, are protected. If you need to know the difference between mouse dropping and bat dropping, just pinch it between your fingers. Bat droppings are made from the remains of insects and just crumble away to nothing. Mouse droppings don't. Now, if bats are present, treat the timbers when the bats are active, when they can fly about and get away and go somewhere else. They'll come back in their own good time. And specify bat-friendly materials, and Mrs. Google will tell you as much about that as I can. Onto some pictures. We've got Deathwatch beetle on this side. We've got common furniture beetle on the other side, my assistant's fingers. We have, at the bottom picture, timber that's been damaged, but the heart of it's still fine. So it is damaged. In that particular case, there's no active, it's the same beam as the fingers are on. Those furniture beetles are not active, and we recommended no particular treatment. We're not replacing the timbers there. Right, on to cracks. Are we doing all right for time?
Yeah, good, thanks.
Yeah. Cracks, including obviously subsidence. First, just think about what's causing the crack. Is it expansion? If so, it might be water content, might be freezing, might be rust. Amazingly, iron, when it oxidizes, takes up 7 times the volume that it did before. It's awesome, the power of a rusting piece of metal. Sulfates, I'm not going to go into much detail on sulfates, but where we come across sulfate damaged brickwork, it is a real difficult problem, and it needs a proper technical look at. You'll know when you've got it because you'll be able to stick your penknife in and it's gone soft, it's lost its integrity, it's gone almost pasty inside. Vegetation, of course, roots and things, expanding walls. It could be contraction, that could be fresh concrete contracts, and calcium silicate is it's unusual, but it does. Shrinkage, if you've got roots taking moisture out of soil, there'll be shrinkage underneath your building. Clay and peat clearly swell and shrink as the moisture in the ground changes. Groundwater, big influence on those factors there. And timber decay, of course, if you've got structural timbers and they decay, your building will shrink. Settlement, we've got loading, abnormal load, loading with additions to a building, that kind of thing. Compressible ground, and removal of support. Now, removal of support, I've already said, is often by water moving underneath, removing the fines from the ground underneath your building. So always, when you see it, consider springs and broken pipes. Could be a broken drain, could be a broken main. Now, where you find irregular cracks, you've got to work hard to find out what the solution is. It could be differential support. So you might find there are stairs giving a little point of support to a building. You could find a crack tracing a flue where there's less support. It could also be drying out cracks. Very often in renders and things you see a lot of irregular cracks which are likely to be drying out. Not so much in heritage property, but irregular cracks are found when you've got cavity wall failure as well. If you find you've got a horizontal crack high up, think roof spread, think parapet failure. If you've got horizontal cracks repeated down the building, think wall tie failure, clearly if it's brick. If you have a horizontal one-off crack, look for materials differential, old lintels, timber failure, corroding metal again, a slip plane, something different about the masonry below and the masonry above the crack, giving you a slip plane, and normal thermal movement not having anywhere to express itself and so making a crack. If you've got horizontal cracks low in the building, look for a slip plane at the DPC, very common. Look for sulfates below the DPC. Look for thermal movement, look for moisture movement in the ground, and look for subsidence. Where you've got vertical cracks, the giveaway next to a corner or spaced 7 to 10 metres along a building, it's likely to be thermal expansion. Could be moisture-related shrinkage. If you've got vertical cracks at junctions and Risbon joints where new masonry is joined to old with a clean joint, well, that's going to be differential loading, differential settlement, could be water seepage. Inside the building, if you get to a corner and you find that perhaps a partition wall has dropped, you might want to look at roof spread, you might want to look at differential settlement, but very often it's removal of support. And what day is it? Earlier this week I was in an old post office and looking at the accommodation above the post office. It's a listed building, and I was seeing at the internal wall little tears in the wallpaper, and sure enough, at some point they've removed walls to make the post office space and the ground floor bigger, and they've done nothing about supporting the partition walls. They don't need a lot of support, it's only a stud, but obviously it's inadequate because I'm seeing the cracks. Diagonal cracks, really these are our favourites, I think. They're often full height, and you get some corkers when you've got foundation failure, ground failure, clay shrinkage. Again, removal of support and broken drains. Sometimes removal of lateral support. If we've had a row of buildings, a terrace of buildings, and something's removed, there's no longer any lateral support, you get a diagonal crack. Impact damage, surprisingly common actually, and vibration. When you find cracking, particularly diagonally cracking, we're working on a building on a main road in Richmond, Yorkshire, and it's 400 years old, and we're finding cracks due to vibration. The building wasn't built for the kind of vibration it's getting these days. Diagonal with misalignment, you start looking for rotation on slopes, landslip and heave. I've got an if time note here, but I think I'm going to skip it. Very, very quickly, there is a way of actually pumping hard plastic foam into a localized subsidence and actually jacking the building back to where it should be. If you need to know about that, we can talk about it after. Pointing and renders and the use of line. This is a huge topic. The essential rules are that pointing must be softer than surrounding masonry, and this will rule out cement-based mortars for many types of stone and brick. Renders, no thicker than is necessary, should finish at a bell cast short of the ground, should be applied in layers to keyed surfaces, and again be flexible and breathable. These last two make cement-based renders unsuitable for most traditional applications. Flexibility is especially important, and we'll see that in lime in 2 ticks. There's a wonderful picture. It's just opposite our children's school. That is very advanced decay. You're going to have noticed long before that happens that you need to do something. Look for stones just deteriorating at the edges next to a mortar bed. If the stone is being eaten away and the mortar is intact, it's the wrong mortar. It is much cheaper to sacrifice the pointing and repoint periodically, every 50, 100 years or whatever, than to lose the whole wall. And obviously just a little poke with a penknife will tell you what's going on in most cases. And I'm going to skip another if time point just to keep going. We can come back to them if we want to, because I want to get on to lime. Now, Lime is God's gift to man for the construction of buildings. I don't know where I found that quote, but if it's not already attributed to anyone, I'm going to take it for myself. Lime is natural, flexible, breathable, can be made as soft or hard as you need to. It's close-grained, so it's water resistant when the rain's pouring on it, and it wicks in dry weather. In order to use it effectively, you really only need to understand two things: the lime cycle and how to mature lime products, and how to mix lime and therefore how to specify it. So we've got the lime cycle, which is stretched into an oval. It used to be round, and it seems to have crept slightly over into the other box as well, but never mind. I don't know if you can read that, but it doesn't really matter. What we have is limestone, just hewn out of the ground. Limestone, hard, a really good building material. If you burn it, you remove carbon dioxide, and you get quicklime. So it goes from CaCO3, you take away the CO2, and you get CaO. That's quicklime. You then slake. That's a quick process, by the way. It doesn't take very long to do. It doesn't need ages to be. It doesn't take ages to burn lime. You then slake it with water. You're adding H2O. That's another quick process. That brings you back to CaOH2, which is quicklime. I have to look that one up because I could never remember that. Now, you then get to the slow process. Once you've got a mortar, it needs to set slowly. The risks are drying out too fast and freezing. So in both cases, a bit of wet Hessian over your layers of lime will stop it drying out too fast and should prevent it from getting frost damaged. Now that slow process is the carbon dioxide coming back into the lime, chemically, rebonding. So, having gone from limestone through these processes, you come back to CaCO3 once more. It is the same. Chemically, it's the same. So it's the perfect cement. You've got limestone back in all the joints that are bedding your building. So for mixing, your aim is to coat each particle of aggregate in your mix with adhesive material, leaving no gaps. So if you take a known volume of dry aggregate, you weigh it and then measure in water until it's covered, that's the amount of binder you're going to need. That volume of water you've put in is the volume you're going to need of binder. Now if you weigh that volume of binder, you now know how much, you know your ratio between your dry aggregate and your binder. So it's very simple to do, and you multiply it up to make a working mix. I'm obviously skipping what you do if you've got a mix of different aggregates and pozzolans and all the rest of it, but just in basic terms, 3 buckets of mortar will need 3 buckets of sand and your binder. So 4 into 3 does go. You might take 3 buckets of sand, 1 bucket of lime, and make 3 buckets of mortar. Now, NHL hydrated lime comes in different strengths and with different relative bulk densities, so don't just use 3 buckets and 1 bucket. And use the stronger, denser limes as base coats, and in the more exposed work, so chimneys and things, where frankly you're not going to get up and do little bits and let it dry carefully. You've really got to let it go off. So use a stronger binder and a stronger mix. It's really worth learning more about lime and using it more. It's a fantastic material. Right, now we're not going to spend much time on masonry because I'm going to come back to it in the case study. But repairing masonry. Replacement stones. Of course. Why wouldn't you? Perfect. Best repair. Indents. That's cutting back the damaged face and putting in a piece, let's say half a stone thick. Yeah, as required. Indents are fine. Plastic repairs. So that's your proprietary mixes or mix yourself and try and repair your stone. Well, if no other method is available or affordable, then it's better than not doing the repair. Silicone treatments. Never. Never. Stone doesn't mind being wet. There's lots and lots of stones in the ground, in the sea, in rivers. It's wet in the environment. Stone doesn't break down just because it's wet. But if you try and prevent moisture from migrating through stone, the more porous the stone, the less long it's going to last. And we've got some nice examples here. Plastic repair. Are these all Elgin High Street? No, that's not. That's again the house with the big roof, big new lead roof. Plastic repair, it's all right. It'd be better if you could afford to make new stones, as we did here on this chimney. And just while we're on the chimney, those elephant's foot vented caps, that is, in my experience, the best way to cap off an unused flue. Birds can't get in, but the air can circulate. On the right, we've got beautiful line pointing. That's line putty pointing. Really fantastic, but it misses the point. What we have there is the front of a shop falling forwards towards the high street because, again, the shop's been opened up over the years. People have knocked down walls and whatever. Now it's got no, well, it has now, but at the time I took the picture, it had no restraint holding that facade back onto the building. It wasn't in any immediate danger of dropping out, but it is now restrained back through the walls that hold the whole terrace together. Don't miss the obvious. And this chap down here with the yellow shirt, I know him very well. He's preparing for indents there. He's got a Kango and he's breaking off defective stone to half the depth of the stones on this building, and then of course new pieces have been cut elsewhere and coming to be put back in. Right, still on time?
Yeah, 10 minutes.
Ooh, right, rising damp. It is of course water rising in masonry by capillary action. It rarely occurs above a metre, does sometimes. Absent physical barriers, DPCs and floor membranes, what can you do? Well, you can inject silicone DPCs. You can do electro-osmosis, and you can use Narpan siphons, or in my opinion, you might as well use aromatherapy. Now, I do want to just break at this point and talk about measuring moisture. The definitive test is an oven test. You take material, send it off to a laboratory where it's weighed, oven dried, weighed again. That is definitive, but it takes too long. It's not practical. Conductivity. I use the cheapest, nastiest damp detector there is. It doesn't matter if I leave it somewhere then. It doesn't have a little meter. I don't have to go in a dark cupboard and try and read it. Reading it would be pointless anyway because they're only accurate in timber. Damp meters, all your protometers and whatnot, my assistant has one, they're only accurate in a timber yard. Great for if you're a sawmiller, fantastic tool, but for detecting damp it's rubbish. For measuring damp it's rubbish. It's as good at detecting damp as this one. So this makes a nice squeaky noise. The damper it is, the higher the squeak. I love taking this round houses with clients because I poke it in the wall. Ooh, you got a bit of, ooh, ooh. But it's not reliable, and I'm going to have to come off here to show you why. So I'll just shout. The first thing is, if you find what it's doing, of course, is measuring conductivity. It's not measuring damp at all. It's just measuring conductivity. So I've got a piece of, very conductive. Now that might be a foil-back plasterboard, might be hidden behind a piece of soggy wallpaper, like Paul Daniels. Oh! So my meter may or may not It's not going to, but it does sometimes, pick up the piece of foil behind the soggy wallpaper. Another one, absolutely classic. If you've got rising damp, it's going to bring salts, a mixture of salts, this is just normal table salt, out of the ground and into the wall. So when you put your damp meter in, that's just in a bit of table salt. It's confused. It's conducting electricity. That salt is dry, but it's telling me there's a problem. Now, where did that block get to? Right. This is actually not from a coal mining area. It's from the Scottish borders, but it's made with ash. Ash contains carbon. It says this, my meter, tells me it's screamingly damp when it isn't. It's perfectly dry. Lives by the stove in my office. Just for days like today. So, you need something that's in between the laboratory test and the handheld meter, the speedy. I think probably we'll stop dealing with the metering now, but anyone who wants to see the speedy and know how it measures by, you put here we are, calcium carbide with a known measure of stuff you've drilled out of a wall. You drill it onto tin foil so that you don't touch it. You put it in this chamber. You mix it with a bit of carbide with the lid on. The carbide extracts the moisture and makes acetylene gas. The acetylene gas comes out, puts up the pressure, you read off the pressure on the bottom. Absolutely reliable. All of us expert witnesses use this, and if you don't use this and you are an expert witness in a court case, frankly the other side will defeat you, because this is taken as the definitive test. So, the reason why these things don't really help, if you look at the top right picture, that is, it's only a diagram, I couldn't find a photograph unfortunately, what happens if you take a damp brick. A damp brick might have been sitting in groundwater for 100, 200 years. Every tiny little pore in that brick will contain moisture. You think you can drill a hole in it and stick some silicone in the hole, and somehow all that water is going to get displaced and replaced with silicone and make a damp-proof course? Oh, come on. What planet are you from? This is the biggest con in the whole world of damp-proofing and building repair. It fingers, like that. The electro-osmosis is certainly not proven, and the little weep holes, well, they can't do any harm, can they? If you just use your brain, if you have a damp building, minimise the water around and under the building, and then detach the linings from the damp masonry and allow the masonry to breathe. A little bit of water in your own environment inside the building is not going to hurt you. I'll come to condensation in a minute. Where that's not possible, you have to devise a physical barrier, and I've just put a full stop there. There's lots of ways to devise a physical barrier, and it would take too long to go into them, but just bear that in mind. The other methods don't work. Now here's a great one. Top left, I'm looking down from a roof between a wall and the strappings on the inside, and I'm seeing material dropping down and bridging. At the skirting board level, down at the ground floor, that's going to be a mess. It's going to bring moisture straight across and into the building, and sure enough it does. The picture below that, the floor inside is below the ground. The vent is below the ground. The same house to the right, this is an internal masonry wall in a kitchen, you can, bottom right there. We've got an internal wall just sopping up moisture from under the building. Now in that case what we did is we took the floors out of the building. This is extreme, but anyway, we took the floors out of the building and we put a whole series of perforated drains following all the walls around the inside of the building, and put modern floors in, and in fact with underfloor heating and various other twists. That building, which was the worst wettest building we've ever surveyed is now a dry building. The picture above, you can't really see very well, but that is a building that was drilled and injected, and that's moisture now blowing over the top of 1 metre of renovating plaster. You can't stop Mother Nature, but you can work with her. Here we have, this is a wonderful building. This is an A-listed Adam mansion house, altered by Lorimer. It was all plastered on the hard, the lower floor. This is the entrance hall. Top left is as we found it, and you can see, I've lost my fishing rod. Oh! Right, well, we can see bits of damp, evidence of. We stripped it. We actually found Lorimer's original drawings before starting the work, and we knew that he planned beautiful pedimented doors, and we brought one of his own fireplaces from a Georgian room where it shouldn't have been down into this hall. The bottom right picture is of it finished. So it's been stripped, strapped, an exact replica of the plaster has been put back but dry, and there's ventilation going in behind the skirting and out at a line you can't see. It's obscured behind a little fillet. Absolutely fabulous piece of restoration work in my view. Other penetrating damp. If you've done everything so far in this talk, you won't have penetrating damp, so we don't need to worry too much about that. Condensation. Condensation is really rarely a problem in traditional structures unless inappropriate works have been undertaken. But when you find it, minimise sources of moisture, minimise cold spots, and increase the number of air changes, and then you won't have condensation anymore. You might not be very cosy, but you won't have condensation anymore. Now that's except interstitial condensation, which is a really unique and difficult problem. We've mentioned interstitial on flat roofs, but here are two buildings that we're working on. Again, they look a bit upright in this picture. They're slightly broader than that in real life. Now these are both concrete structures. We've got the Spanish city at Whitley Bay and the Palladian mansion by Adam that was altered by Lorimer in the previous picture. Now the difficulty we've got here is, and these pictures won't come out terribly well, but you have a temperature line and an RH, relative humidity line. And here, this is the building before we started, they meet. That's dew point. That dew point is happening in the concrete, and in the concrete is all the steel that's keeping the concrete together. We know that if it rusts, it will occupy 7 times the volume that it did before. We know it will blow that roof to bits. So, we've put a vapour barrier in. We've slightly changed our materials around. But that vapour barrier banishes the dew point to just outside the lead roof on the top. Just outside. It's all we could manage. Now, the condensation is not happening in the concrete. That building is a lot safer. We had to use an extraordinary product, details of which will be available after the show. We still all right? Case study?
Yeah,
Couple of minutes. Couple of minutes! Right, case study. This is a bridge, also said to be by Adam. The photograph, black and white, taken in 1963, the colour one taken a couple of weeks ago. It's like a Christmas cake with all the icing falling off into the water. Now, what we've done is we've scanned this bridge in 3D to a very high resolution, less than a millimetre. So every aspect of that bridge, every stone, every mortar bed, every defect is scanned, and we have a point cloud, a very dense point cloud, which is a digital jelly mould. Now, what we do with that, we use digital jelly mould, we convert the drawings to 3D on CAD, and then we create an STL file for each stone we need. Now, an STL file is a 3D file which drives a computer-aided CNC cutter. So one of these marvelous new cutting machines that is instructed, is computer-driven rather than human-driven. So there's an example that's easier to understand. And here, we won an award for this. This is putting a new white limestone staircase into an A-listed building. 3 flights joining 4 stories. An extraordinary commission. Now, this wouldn't have been really possible without the CNC cutters and the technology that drives them. That just gives you a little flavour of what it was like to build. The picture here is the one I want you to look at, really. That stone is just off the CNC machine. It's still got to be finished by hand, but lovely. It's already got the scallop at the back. It's already got the bullnose and covetto. It has taken so much work out of preparing this staircase. What did we need? 67 stairs, I think. Wouldn't really be possible. Now the impossible. That client said, oh, if you can do that, I've taken a picture of a fireplace I can't afford in an antique shop. Here's the picture. I've got some measurements as well. Could you make me an exact replica except have our family crest on the front? Now that is designing in 3D, which is a slightly different task, and it takes a long time. It's difficult to do. But you can see the palette of goods when it arrived are absolutely fantastic. All that detail cut by a CNC machine, a different CNC machine, and then finished by hand. And I haven't actually brought a picture of the finished fireplace, but it's wonderful. So what we aim to do is we aim to buy block and cutting time. We're not interested in paying bench masons. We love bench masons, but not for this. So we scan the structure in 3D, very high resolution. We auto-correct and prepare it for CAD. We use CAD to draw the replacement stones. We code, in fact, yellow for repaired stones and blue for new stones. And then we explode that drawing, put a back on all the stones using the CAD, and that converts to an STL file for each stone. So for the bridge, we're going to need 250 or 300 stones. We will have a 3D drawing for every one of those. Now, if we send that pack of 3D drawings off to a yard with a CNC machine, they will calculate how much block and how much cutting time. And the great criticism of this is that it de-skills the crafts. And I say, well, hang on a minute. I can probably do 10 bridges a year if I use this technology, and only 1 bridge a year if I don't. There aren't enough masons to do 10 bridges from first principles. Hand sawing every stone in the cold, that's not, you just don't want masons to do that anymore, and they don't want to do it either. Now that's really the end of it. If we've got 1 more minute?
Yeah, 1 minute.
1 minute, right. This 3D scanning thing is utterly amazing. I quite like those drones that people fly around taking pictures of the tops of buildings. I think that's interesting, but I think this is utterly astonishing. If we create a digital jelly mold for, in this case, very high value ceilings, museum quality ceilings, they're put in by Thomas Claydon in 1750. Actually, the ceilings aren't shown here, but the walls are, and it's the same hand that's done this plaster work. And some brilliant Duca's carving on this organ here. If we scan that in 3D before we start work, we've been working above these plaster rooms. We've been doing hot works, wet works, and heavy structural works. And if we lose a piece of that plaster, we can send a piece of our scan to someone who's got a 3D printer. They can print it in plastic. We can put a latex over it, get a resin, get a mold out of it, put our plaster in that. We can actually put our piece of ceiling back exactly as it was. Interesting from my perspective as a practitioner, but just think about the insurance. The insurance industry should be demanding that our best buildings are all scanned. You get everything. You get the metal work, you get the plaster work, you get the timber work, you get everything as a dense point cloud. It's a wonderful thing. So I think I've probably kind of rambled on enough. If there are burning issues, raise them if there's time.